Hello. Okay, so today we've got George Trimble with us. I want to thank you, George, for joining us. He is going to present part 2 of geocentrism. Part 1 was very, very interesting, so I'm looking forward to part 2. Thank you, George. I'm going to go ahead and turn it over to you.
Well, thank you, Amy. Welcome, everybody. It's been a while due to this rotten COVID crisis. We left off looking at a model of the universe called geocentrism. It's the idea that somehow the Earth is at the center and everything else is going around the Earth. And while it is wrong, obviously, we all know that the sun is the center of the action. It's very informative, and it'll hardly steer you wrong. It took 2,000 years, in fact, for the geocentric model to kind of fall apart at the hands of Copernicus and Kepler and Tycho Brahe and other great minds who found small details that didn't fit and forced a rethinking of the model that we based our astronomy on. But for the most part, the geocentric view is more amenable to wrapping your mind around because for all the world, it looks like the Earth stands still. Doesn't it feel that way? I mean, the sun seems to go across the sky. It seems to be in motion, and we seem to be still. And so it's a more intuitive viewpoint. And as you'll see, it's a powerful viewpoint, and it's a great springboard to get to the next level where we understand elliptical orbits and the Earth in motion and other complexities. So from a learning point of view, geocentrism is a good starting point. I'd like to thank all of these groups that you see listed on your screen for their collaboration in putting together the Geauga Sky Watchers, where our motto is, "We look up." Let's get started with a little recap. There we go. I'm hearing some background noise. Has somebody got a TV on?
I think I found them and muted them here.
Okay. So here we go. Geocentrism, a springboard to Copernicus, viewing the universe through the eyes of ancient observers. So first, let's do a little recap. What have we established in our first part? We established that the Earth is not the center of the universe. And while wrong, it's an informative view. We decided that just by looking up, that the celestial sphere is the best model for understanding the motion of the stars. They seem to roll around the Earth glued to the inside of a giant celestial sphere. We did away with the idea that potentially it could be a giant celestial barrel. We discovered that the sun's first motion is the very same motion that is most obvious to all of us since the day we noticed the sun. And that is that it rises in the east and it sets in the west, and it seems to cruise across the sky throughout the day. We made some observations, and we decided that the size of the Earth is small compared to the universe at large. And we'll flick through a couple of those slides to remind you of what premises we made and conclusions we drew. We decided that the shape of the Earth is round based on some observations. All of this is important basis for deriving some of the important stuff that we do later in the talk. We decided that there's a second motion to the sun, a motion whereby the sun seems to fall back from west to east over time throughout the course of a year, completing a complete backwards circuit in 365 and approximately a quarter days. And this we call the second motion of the sun. And finally, we found that the sun seems to wag back and forth on the horizon. It rises and sets at a different location throughout the year, wagging back and forth across this center point which identifies the moments of the equinoxes. And the excursion, the maximal excursion north and south, as we look at the rising location in the east of the sun or the setting location in the west, the maximal excursion defines the moments of the solstices, the summer and winter solstices. So this is the third motion of the sun, and it's where we left off. And quickly, we're going to flick through just a few of the slides that we previously covered. The sun rises in the east and sets in the west. This is the most familiar of these motions, and this we call the first motion of the sun. That's a view looking south. We note that the stars rise and set. It's much the same as the sun. When the sun sets, we see that the stars pop up in the east and grow brighter as the sun's light dims with dusk. And the stars too follow paths through the sky as they head west and sink into the utter west at the end of the night before the sun rises again in the east. And we took note that the stars always follow the same track, parallel tracks through the sky. The sun, however, doesn't stay on the same track each day, as I mentioned earlier. So the question becomes, why does the sun follow a new track each day? I hope that we discover that today. Here we have stars rising in the east, and then on the right, you see stars setting in the west, and they create these parallel train tracks in the sky when we look at time-lapse photography. We note that there's an order, a celestial order. The stars always rise in these identifiable constellations that don't change with respect to each other. The positions of the stars stay the same over measurable time, and they make these shapes in the sky that we recognize as Aries, the ram, which always rises before Taurus, followed by Gemini, then Cancer, then Leo, etc. These 12 constellations that we recognize, through which the sun appears at some point during the course of a year. These are the stars and constellations of the zodiac. Now, we got rid of the celestial barrel hypothesis when we saw this picture, noting that stars, when looking north at the pole star, the North Star, tend to go around in a big circle. And so the barrel seems closed at the top, and we landed on the hypothesis of a celestial sphere based on this. And so we came up with this idea of the Earth, shown here in green, floating in the middle with its north and south celestial axis in alignment with the celestial sphere and its axis, with the stars rotating around the Earth once every just short of 24 hours, as we'll soon see. Here is a picture that shows us that our hypothesis that the Earth is but a point compared to the rest of the universe. This is a Voyager image taken as it was passing under the rings of Saturn, looking back at our little pale blue dot located here. That's Earth, just a dot, almost nothing in comparison to the size of the universe. We decided that the shape of the Earth is round, and you see here that the moon has a shadow of the Earth cast on it during an eclipse, and that shadow is round. And it gives a hint that the Earth is casting around shadow because, in fact, it's a sphere. It's not a flat disk. It's not casting a line like you might expect if it were an edge-on coin. We also took note of the following set of pictures. Assuming that the Earth was a flat disk, what would sunrise look like? Simultaneous for everyone everywhere. And if the Earth was the shape of a dish, sunrise would be opposite. It would be seen first in the west and then in the east later in the day. But the Earth is round, and as a result, we see sunrise first in the east and then in the west, and we report time differences for events, celestial events, because of this. And of course, there's evidence that's over 2,000 years old, first noted by Hipparchus, that ships sailing away at sea tend to sink into the horizon as they get further away. They don't just get smaller, but they seem to sink down because they are disappearing over the curvature of the Earth. And as a result, our line of sight is blocked by the surface of the Earth. Now, on to the second motion of the sun. I'll remind you that if you look south at noon, when the sun is just at its highest point for the day, and it's the hottest moment of the day, and if you could just dim the sun enough to see a star that happens to be at the same meridian or the same longitude as the sun at that moment, and then close your eyes and wait until 23 hours, 56 minutes, and 4 seconds passed, this is the picture that you would see. That star has set in the west, gone around under the Earth, risen in the east, and come back to the meridian due south of you after those 23 hours, 56 minutes, and 4 seconds. But what happened to the sun? It too was dragged around by the rotating sphere of the stars, the celestial sphere, but it seems to be dragging its feet. It has the brakes on if you follow my meaning. The sun takes an additional 3 minutes and 56 seconds to reach the center line. It shows up late by 3 minutes and 56 seconds every day. That's equivalent to almost 1 degree, which is why the sun it falls back 360 degrees all the way around. It shows up late over the course of 365 and a quarter days. You see, it's falling back, and that's what defines a tropical year. It takes 365 and a quarter day to fall back to its original location. So that's the sun's second motion, and it's less apparent. You have to be careful to catch that, to find it, to understand it. But it's for that reason that different stars are apparent at different times of year. Currently, the sun's close to, for example, Gemini. And so we can't see the stars of Gemini because they're in the daylight. The sun washes out the delicate light of those stars. And so we see different stars at this time of year, Libra, Virgo, and other constellations. But because the sun is moving with respect to the stars and falling back in its second motion, we're able to see all of the constellations. We just have to wait a year to see them all. Now, watch this series of pictures here and note how the sun is falling back. Here we see I use symbols instead of actual little dots for the stars. This is the symbol for Pisces. And so the stars of Pisces are rising. This is looking east just at sunrise, looking east just before the sun comes up. The last stars you see before they wink out are the stars of the constellation of Pisces. A month later, you see Aries appear before the sun rises. And then Taurus. It's slipping back. It's exposing a new constellation each month. These are called heliacal risings. There's Gemini and Cancer and Leo. I'm sorry, that is Leo. And notice that the sun is going to follow the same path as Taurus for the day, actually for the month. And now you see that Virgo appears, followed by Libra and Scorpio and Sagittarius. The sun is showing up late, allowing a new constellation to appear on the horizon each day. Aquarius, and back again is Pisces. Now, the second motion is the falling back motion. But if we flick through these quickly, I want you to see the wagging side to side motion. It's the third motion. Now watch. You see the sun wagging back and forth on the horizon? So now we've discovered, we've discovered a third motion of the sun, this wagging back and forth. The sun seems to rise more northerly when looking east in the summer and more southerly in the winter. And as a result, the arc it makes in the sky is different. In the winter, the arc is low on the horizon. It's short, and the days are short, and the nights are long, and it's cold. And we're going to see why shortly. In the summer, of course, the sun rises more northerly, and as a result, it spends more time in a larger arc in the summer in the daytime than at night. So we have this second motion, this counterclockwise motion, and from these pictures that we just saw, but we also have a third motion, this wagging back and forth. Now, if we were to chart the location of the sun day by day throughout the year, noting, look here on the left, we have declination, that's the height above the celestial equator, which is noted here at 0 degrees right here. Can you see that? 0 degrees. And here we have right ascension. This is equivalent to longitude. And it is longitude in astronomy isn't based on Greenwich like on Earth, because there's no Greenwich in the sky. That's in England. So in the sky, we have to pick another random point to base the longitude measure from. The celestial longitude, also known as right ascension. And that point is the moment of the equinox, of the vernal equinox. That's the moment when the sun is coming from the south, that's northern winter, crossing the equator, and now we see the sun higher in the sky each day as summer approaches in the north. That moment of crossing the equator, that's called the equinox, when days and nights are of equal length. And it's from that moment, it's when the sun is located at that point that we define 0 hours for right ascension. And right ascension, for whatever reason, is not in degrees, it's in hours, but we can make them equivalent with simple conversion factors. But whatever the case, we measure right ascension in hours and declination in degrees. Now, the place in this, the place where the sun is located with respect to the stars from our viewpoint, at the moment it crosses from south to north, at the moment of the equinox, the vernal equinox, the vernal equinox, that's spring, it's amongst the stars of Pisces. So we don't see that constellation because it's a daytime, the sun's blocking out the stars of Pisces. But using creative techniques, we can figure that out. And so what we have here is a graph. Each little yellow dot along this sine wave in orange, I should say yellow-orange sine wave, each little dot comprising this sine wave is the sun on a given day of the year. So there's 365 and a quarter right there dots. And notice that the sun is going up and down with respect to the 0 line, which is right here. And its greatest extent is seen here in Sagittarius and here around Gemini and Taurus. And it passes through these constellations labeled in gray or colored in gray. And these are the special constellations that we call the zodiac. They're not particularly any more special than any of the other constellations. Like here's Ursa Major, the big bear that comprises the tail of which is the North Star. They're just groupings of stars, but we call them special because the sun makes an appearance throughout the year along this track and through these constellations. And so the ancient people divided these 12 constellations, they divided the year by 12. And so we have 12 months as a result. You see that? It's pretty cool. But we see this sine wave and I ask, what does it mean? Can we make sense out of it? And I want you to see something so cool. I'll show it to you here in just a minute. I want you to see something that'll blow your mind and help you to understand what that sine wave means, okay? Keep this picture in mind. Now we're on to the new stuff now. As of that last slide, we're now on to the new stuff. So we have this third motion, which we describe as an oscillation on the horizon, and it causes the noon sun to be higher in summer and lower in winter. And its variation is 23.4 degrees above the celestial equator and below the celestial equator. So that's 27 degrees or 47 degrees altogether, right? 23.4. So 47 degrees, close to 47 degrees of total excursion. The extremes, we said, mark the solstices, the crossings of the equator, when the sun is at zero. Let me back up. Like right here is a moment when the sun is at zero. And right here, the sun is at zero. And if you wrap it around, that's here as well. So there's 2 times in the year when the sun is at the zero declination. And those are the equinoxes. We talked about 12 constellations in a year. And it's interesting that these divisions, these equinoxes and solstices, divide the year in 4 parts, in 4 seasons. You got the hot season and the cold season and the transitional seasons. And it turns out that these moments, these special moments, divide the year equally in 90-degree increments. Now, when we look at the stars circling around us and we ask in which constellation is the sun during these special moments, what we find is the sun is exactly divides the circle of the stars in 4 parts of 90 degrees separation. By counting constellations, by looking at the time from the vernal equinox to the moment of an event. Now, this is very important, as you'll soon see, because we'll come across something called the solar anomaly, which was discovered by an ancient thinker by the name of Hipparchus, who later gave us something called precession, the precession of the equinoxes, which, by the way, is why we no longer say that the sun is in Aries at the moment of the vernal equinox. We used to call it the first point of Aries. That was the start of the celestial year. It was the moment from which all other longitudes in the sky were marked. But this has been slipping. We're now in Pisces and we're moving into the age of Aquarius. You probably have heard that ancient 70s song, The Age of Aquarius. I'm not going to sing it to you. I'll just embarrass myself. But what we find, I see some people laughing down there. What we find is the sun is not confined to one track. It's moving around, it's misbehaving, and we have to understand how. To fully understand the sun's third motion, we will require that we first invent the tools to describe it. We need to invent declination, and we need to understand right ascension. How do we discover where the sun is amongst the stars at these celestial moments? And that stuff can be kind of complicated. And so in order to abbreviate this talk just a little bit, I've had to do a little bit of hand waving. And some of this stuff can be saved for another talk in another time. So let's draw a few conclusions here. We've made some observations, just laying in the grass and looking up and seeing what is the sun doing at what time of year. And we hypothesized a model, that model being a small Earth, a stationary Earth, a moving sun moving in circles around the Earth, a celestial sphere, a spherically oriented rotation around the Earth at its center, along which are carried the stars and which drag the sun along with. And we've come up with this pretty complex model for just laying in the backyard, staring at the sky. Now, we can ask questions within this model and impose some geometry and ask, does the predictions that our model makes based on the geometry that we do, does it accord with reality? Do we make good predictions from our model? For example, we can ask the question, if in fact we take all of these assumptions, what can we discover about our latitude? And is it right? And for example, which stars can we point at in the sky and say, those are on the celestial equator as they rotate around Earth? Well, I'll show you here. First, we have to make a simplifying approximation. We're going to assume, and by the way, if you have questions, jump right in, okay? Just unmute and jump right in. Let's assume that the stars are close. If in fact they're close, like this first picture here, then an observer in the North Pole and an observer on the equator would note that a star has a different angle and that the light rays are arriving at Earth from different angles. And so they would each report that the star has a different angle from the surface of the Earth. But if we move the star farther and farther and farther and farther away out to infinity, what happens is these light rays become essentially parallel, no matter where we are on Earth. We measure the same angle to that star, and we see that the light from the distant stars rains down on Earth in parallel rays. And it turns out this is exactly what actually happens. And so we can actually do a measurement standing in New York and do a measurement on stars in Florida, and everybody agrees. And so the light is raining down parallel, and therefore we assume that the stars are very far away. We are going to assume that the light is parallel, although it is not. It's just very close to parallel. But in the limit of infinity, as we say in calculus, it's essentially parallel rays. So what can we do with this? Let's draw this picture here. This is the Earth in the black circle. And we have the North Star here, the red one. And the light from the North Star, shown in red, is raining down everywhere on Earth in parallel rays. Okay. Of course, this star is drawn too close, but we know it's up there very far away, raining light down on Earth. Now, we have an observer, you, standing here at your latitude, wherever that is, presumably somewhere near Geauga County or Cleveland. And the light ray that interests this observer is this one right here that I'm dragging my mouse across. Can you guys see that? You see? Okay, I don't know if you can see my mouse moving.
Yes, yes, we can.
Good. So this observer is interested in that ray of light because it's the one right where he is. It's the light ray he can measure. And he does. He takes a measurement. He measures up the angle from the horizon, which I've drawn as this black line tangent to the surface of the Earth. He measures up from the horizon and measures the angle here, which he labels alpha. I don't know, 30 degrees, 40 degrees, 50 degrees. He measures some angle, and that's the angle from his horizon to the light ray. And he says that star, the North Star, is alpha degrees up from my horizon. Now, he also draws in his mind, he draws this line here through the center of the Earth, from the center of the Earth, through his location, and extends infinitely up above his head, and he calls that the zenith. It's nothing more than the place straight overhead. That's where, if birds poop, it hits you on the head. Okay, that's the zenith. Now, because his zenith makes a 90-degree angle to his horizon line shown here, we know that this from here to here is 90 degrees on both sides of the zenith. And so the angle beta which is defined by the light ray from the North Star, and the zenith, this angle is 90 minus alpha, because alpha plus beta has to equal 90 degrees. Do you see that? All right. Let's take a few of these lines off to the side and look at them separately so something becomes apparent. I'm going to take the light ray from the North Star, and you notice here the dotted line shows that it's extended down to the equator of the Earth, inside the Earth. And I've got the zenith line crossing the light ray, extending to the center of the Earth. And you see that it creates a giant celestial triangle within the Earth. I should say a terrestrial triangle down inside the Earth. And I love triangles, particularly right triangles, because we could do some trigonometry on right triangles and we can analyze them. But what can we say about this angle here at the top, right here, right there? If this angle is beta, when two lines cross, alternate angles are equal. And so this is also beta. So let's take this down to this next picture down below and see that this triangle formed has angles defined as beta right here, which is 90 minus alpha, 90 degrees by definition, it's how the triangle was constructed. And this final angle is the latitude of the observer. By definition, latitude is defined as the angle from the equator up to where you're standing. That's your latitude. And we can solve for latitude because we know that all angles of a triangle add up to what? 180 degrees. They do. Okay, so the latitude is equal to 180 minus the 90 degree angle minus the 90 minus alpha, which when we distribute the minus sign, this get a little tricky algebraically, but we have to distribute that minus sign into 90 minus alpha, so it becomes alpha minus 90. I'm sorry, did I say that right? Let me see what I've done here. Minus alpha plus 90. What have I done? Let's see. Latitude equals 180 minus 90 minus 90 minus alpha. Yeah. So minus 90 minus alpha plus 90, or yeah. And so the 90s cancel out and you get 180 minus alpha. I'm sorry, they don't cancel out, they add together. There we go. And so we get 180 minus alpha. There we go. And so the 180s cancel out and what we're left with is alpha. I'm sorry, I tricked myself there trying to figure out what I was thinking. But the end result, the end result is your latitude is just alpha. That's the original measurement you made on the North Star. So you see, when you measure the altitude of the North Star, you're measuring your latitude. Now, when we measure our latitude in, say, Cleveland or close thereabouts, the altitude of the North Star is 41.5 degrees. And that's exactly what you would expect if you're standing on a spherical Earth that's small compared to the solar system and small compared to the universe. And if the stars are far away, all of our presumptions are yielding accurate data that's verifiable. You can go outside and measure the altitude of the North Star and discover that it's your latitude. You're standing at 41.5 degrees north latitude. And that's how high the star is up from the horizon. You can do that using a protractor and a straw, but you'll have to look that up on the internet. I don't have my little device with me to show you. We've got a little, wonder if I can get rid of this yellow mark on the screen. All right. So the second question is, where's the celestial equator? Which stars are on the celestial equator? Let's place a star on the celestial equator, and again, we'll make the assumption that, there we go. We'll make the assumption that the light coming from that star hits the Earth from its very distant location in parallel rays. And this ray here is of interest to our observer. And he measures the altitude of that star above his horizon, and he measures it at alpha. And again, he subtracts from 90 to get this angle, beta equals 90 minus alpha. And he takes a little bit of a few of these lines off to the side, and he does some cool geometry. He understands that two parallel lines, this line here, the one he measured, and the line from the star that goes through to the center of the Earth, this one here, well, they're parallel, and two parallel lines crossed by a transversal create alternate interior angles and corresponding angles. So that if this is beta, then this is beta. And that's interesting because that's the latitude at the center of the Earth. And so the conclusion is that any star that measures alpha degrees up from the horizon such that 90 minus alpha is your latitude. In other words, any star whose angle you take when subtracted from 90 equals your latitude, 41.5 degrees, you know that star lies on the celestial equator. And we can restate that condition as 90 minus alpha equals latitude, or alpha, the measurement is such that 90 minus your latitude is the measurement. So all stars that measure 90 minus 41.5 degrees for you at your location, those stars all lie on the celestial equator. So if this is, does anybody know how I can get rid of these stray marks?
I don't. It may be when you originally put this together.
Yeah, I went to the pen marker. Doggone it. I got a laser pointer. All right, I give up. I'll leave it alone. But so here's the sky in a time-lapse view, and some of those stars lie on the celestial equator. We just don't know which ones until we measure them. And there's the line that defines the celestial equator. It turns out that some of the stars in the belt of Orion, for example, lie on the celestial equator. That's powerful information. And it's because we know which stars are on the equator that we know which stars are above and by how much, and below and by how much. That defines declination. And it allows us to make that chart that I showed you previously with the sun as a sine wave through the constellations. We can make a chart like that because we can measure the values of the declination of stars. It turns out that if 90 minus alpha is smaller than our latitude, then the star is above the celestial equator by the difference. And if 90 minus alpha is larger than your latitude, the star is below the celestial equator by the difference, so that the sign of the declination indicates the hemisphere. And so we can assign each star a height above or below the celestial equator. And the celestial equator is, of course, an extension of Earth's equator out into space. So we can now assign every star a declination. And the star's declinations don't change over measurable periods of time. Over eons, they do change. There's something called proper motion, but for the most part, the shapes of the constellations stay the same over hundreds of years, thousands of years. Now, this gives us justification for creating that chart that I showed you before. We have not yet described how to assign each star a right ascension, which is a longitude in space, because we don't know how to find the moment when the sun crosses from south to north at the moment of the equinox. But there is a way. The ancients discovered it, and it's just too complicated to describe in this short presentation. It deserves about an hour unto itself. So we're going to skip that. But what about the sun's declination? It's changing daily. Daily observations of the sun's altitude above the horizon at noon, looking south, that's the moment of meridian passage when the sun crosses your meridian. It reveals that the sun is wagging up and down by 23.4 degrees above and below the celestial equator. And it's wagging from side to side on the horizon at sunrise and sunset for the very same reason. Each day changing its sunrise location or sunset location. And this is the sun's third motion, and it explains why the variation and it explains the seasons. The sun is not on a fixed track like the stars. You see, here's you, idealized here, standing looking up. And in June, during summer, the sun rises in the east more northerly than it does in winter. And so its arc through the sky is longer before it sets. And then it's got a little short arc down here for nighttime, which is why nights are shorter than days in summer. And here in the winter, the sun rises southerly in the east, more southerly. Notice it's wagging back and forth through the year on the horizon. And it rises and it sets quickly. It follows a short, low arc in the sky. And therefore, there's less sunlight hitting the northern hemisphere because the sun spends all of its time down here, a long night in the winter. And for people in the southern hemisphere, that's summertime because, of course, they see the sun for a very long period of time during the day. But you see that this most northerly extension we know as the Tropic of Cancer. The sun is see, here's the North Pole right here in the South Pole. And the highest extent for the sun is called the Tropic of Cancer. On that day, its path through the sky is along the Tropic of Cancer, and here, the Tropic of Capricorn. Now, these times, these special names, Cancer and Capricorn, harken back to a time when the sun was amongst the stars of those constellations at that time of year. But now, because of this idea of precession, these moments occur when the sun is in Gemini and Sagittarius. And of course, this middle one here, the sun spends equal time above the horizon. When it rises due east and sets due west, and it spends as much time in the night underneath us. And so these are called the equinoxes, equal night, Latin for equal night, equinox. And it's this moment when the sun, as it's wagging back and forth throughout the year, the moment it's moving from winter to summer, when it's at the due east location for rising, it's that moment that we define as Greenwich in celestial terms. That's the position amongst the stars that we count as the zero location, like Greenwich in England is for longitude on Earth. So we say that declination is to latitude as right ascension is to longitude. We talked about Greenwich being Earth's arbitrary starting point. We call this the first point of Aries in celestial terms. And it turns out that it's no longer in Aries at this moment. It's slid back into Pisces on its way to Aquarius. But why? We have to discover something called precession of the equinoxes to understand this mystery. We know that the Earth is rotating. It's why we have the first motion of the sun. The Earth is turning, and so the sun appears to rise and set. But like a top spinning, if you spin a top, it's turning, but it's also particularly as it slows down, it starts to wag in a circle. Have you noticed this? We call that wagging precession, and it causes the stars to appear to wobble over time. And the Earth's precession has a period of 26,400 years. Its top is not just spinning, but it's wagging in a very slow precessing motion that over 26,000 years causes the North Pole to change, so that now it points at the pole star, the North Star, but it used to point to Draco in a different constellation, or Thuban during the time that the pyramids were built. And so this causes the seasons to slip with respect to the stars. Let's look here. Here we have the Earth. We have the sun at the lowest position. Let's not call this Earth. Let's call this the celestial sphere. If you want to call it Earth, then the sun is really close. It's so close that it's touching the surface of the Earth. Maybe that's a better way of looking at it. And in winter, the sun lies along this line of latitude called the Tropic of Capricorn, and all day long it'll spend circling there. 3 months later, it'll be located along this line of latitude, and 3 months afterwards, it'll be here at the Tropic of Cancer. And then 3 months later, it'll be back there as it falls down into the south again, into winter. And it creates this effect. It's creating a corkscrew. It goes around and around and around the Earth, but as it does so, it goes up and it goes down. And it creates this celestial corkscrew that we see as this sine wave on our graph. Now watch, this is the magic I promised earlier. If we take this graph and cut it out and we roll it into a barrel, I want you to see what happens. Now, what I did here is with my pen, before I rolled it into a barrel, with my pen, I traced out the sine wave, okay? So on the back of this paper, I just held it up to the light and I traced out this sine wave on the back of the paper, okay, for the sun. And then I fold it into a barrel and the sine wave becomes a disc. You see that? It becomes a disc, and its axis, the axis of that disc is off. It points not up and down, but it points off to the side. And that's the axis of the sun's rotation that you saw in our previous slide. See that? The sun is going around and its axis points off to one side, whereas the stars are rotating around a different axis. Here I've traced out the equator, the zero declination mark, or the equator, the celestial equator. And it creates a disk too when this is folded into a tube, and its axis of rotation is up and down. And so these two axes, the sun's axis and the Earth's equatorial axis, are 23.4 degrees separated. You see the angle they make to each other there. And that makes sense out of this third motion of the sun, this variation that we see. So now we can build a model, a conceptual model of the universe with the Earth at the center, with its north and south pole and its equator marked. You see the Earth shown in green. We can circle it with a celestial sphere that turns, as you see by this arrow, on its axes. Here's the North Star right there. Now, you see that there's these little, this bent frame inside our model, inside the sphere. That's going to be the gimbal upon which the sun's sphere is rotating, and I'll show that to you in a second. But let's put the Earth inside. Okay, and now let's look at how the sun works. Now the sun is going around and around daily on its own. It's going daily around with the stars, but it's also circling backwards on its own sphere. You see this gray arrow is rotating backwards, so that the sun, which is fixed on this solar sphere, the sun is fixed on this surface, so that as it rotates, it drops lower and higher. And we gimbal this within our solar sphere, or I'm sorry, our stellar or star sphere, the celestial sphere. You see how it's gimbaled? It's going through little holes in these brackets. So while the whole thing is rotating in red, clockwise, the sun is slowly rotating counterclockwise, so that in the summer, it spends the entire day going around with the stars on that track. 3 months later, it has rotated backwards so that it's lower on its sphere, and it spends the entire day going around with the red sphere on these red axes at the equator, and then like that, back in the back. And so it just keeps doing that little dance. We've created a conceptual physical model of the universe that works to predict the seasons. Now it's kind of complicated, I'll grant you that. And if you had a physical model, it would make sense. You could turn the little black axle backwards and the red axle forwards. And it turns out that the black sphere is rotating on the black axle, one rotation counterclockwise over a year, whereas the red axle is spinning once per day. It's cool that just by looking up and doing some geometry and making some assumptions, we can come up with a physical model that makes predictions, like your latitude, for example. Now, let's see. All right, good. How much time do we have left?
It's about 7:25. So the program goes till 7:30, but we've gone over before, so that's fine.
Okay, well, let me squeeze in one last thing then. And this is kind of important. How do we know the length of the year with any accuracy? And how do we know the moments of the solstices and equinoxes? If I were to ask you, do it, how would you go about it? And keep in mind that this was done 2,000 years ago. And so I decided I was going to recapitulate the efforts of the ancients and measure it myself. So I determined the length of the year by making a measurement of the moment of the autumnal equinox using daily solar altitudes at meridian passage. In other words, at the moment of noon, astronomical noon, I measured the height of the sun above the horizon. And taking my data for the calculated moment of the autumnal equinox and combining it with the data collected by Hipparchus 2,225 years ago, I was able to get an estimate for the length of the year that varied by only 0.002% or something like that. I'll show you later. But it was a very accurate determination of the length of the year. So let's see what we did. In September, here's the day of September, 1617 up to 26. At noon, in quotes, I subtracted an hour, let's see, daylight savings time correction, and I had to make a longitude correction because we're not located in Cleveland where I took this measurement. We're not located right on the meridian that defines our time zone. So there's a little correction that has to be taken into account there. But there was an 81-minute difference between clock noon and actual celestial noon. So I wanted to be taking my measurement at celestial noon. And so here you see in the final column, the value of the height of the sun, the angle the sun makes to the horizon on that day, using what's called a dioptra. It's a measuring tool with a straw and a protractor, and you just the sun shines through the straw and casts a little shadow on a piece of paper, and you can measure the angle it makes. A very simple tool, literally a McDonald's straw and my kid's protractor. So here are the altitude measurements, and I made some corrections for refraction, which they would not have done 2,000 years ago, but I was being detail oriented for my own purposes. But when we chart the data, day versus 90 minus the altitude, that harkens back to those previous slides where beta was 90 minus the measured altitude, remember? Well, when we chart that, look what happens. Where 41.5 crosses the blue graph, it marks the moment, the day of the actual equinox. Now, the equinox didn't happen right at noon, so I didn't measure it directly. I'm finding it from the graph of my actual measurements, which are the little squares on the graph. So, but it happens somewhere around the 22nd, as you see down here. And by charting this within Excel, you can have Excel use what's called least squares regression to come up with a formula for the line y equals mx plus b, and you can actually solve for the moment. So here's y equals mx plus b. We can rearrange that so that we're solving for x and y goes to the other side, and x is the day and y is the co-altitude, and the co-altitude is 41.5 degrees. We plug all that in, and we come up with September 22.4. September 22nd, 0.4 into the day, 40% into the day, which we can further define. 0.4 of a day times 24 hours is 9 hours, and then 0.6 of an hour times 60 minutes per hour is 38 minutes, and 0.4 of that is times 60 seconds, 26.4 seconds. So we have September 22nd, 2015 at 9:38:26 for the moment of the autumnal equinox. The actual moment was actually September 23rd, 2015 at 03:03 local apparent time. And so I was off by 17 hours and 24 minutes, but it doesn't matter. It was within the same day, which is important. And that's all we need, because we're going to compare my moment of the equinox to the moment as determined by Hipparchus some 2,000 years ago. At that time, in his calendar, he noted that on the day of EA 167, epigonomal 1 at noon, that's in modern parlance, September 27th in the year -157, he said that the the equinox occurred at noon. Now that's a very convenient number. Obviously, he wasn't doing a very good job at isolating the exact hour either, but it doesn't matter, because when we take the difference in elapsed days, now what I've done is converted my day, the day I took the measurement, into what's called a Julian day. And I converted Hipparchus's day into a Julian day so that we're using the same calendar. Now we can compare. I can subtract 793,301 elapsed days. And since the difference between 2015 and -157 is 2,172 years, I take the number of days divided by the number of years, and I come up with 365.2403. Now, why this works is because of the averaging effect of so many years. It doesn't matter that the ends are a little ragged. In other words, that our data points end a few hours off. The averaging effect allows us a very accurate estimation of the length of the tropical year. And so actually it's 365.2422. Mine was 365.2403. It's only a 0.0005% difference. Now, what's staggering is that Hipparchus did the same thing 2,000 years ago using 2,000-year-old data from the Babylonians before him. And he came up with the same number. Mine was hardly any better than his. So I think that says a lot about the power of human ingenuity, that the ancients were not unsophisticated, that they were quite sophisticated. And and then we did a summer solstice determination, which requires a slightly different approach, since solstice means the sun stands still. You're not going to see a lot of variation in the altitude of the sun from day to day at a solstice. And so we use a different mathematical technique. We use a little bit of, well, we use what's called the, what's that equation? What is this? Negative b plus or minus b squared minus 4ac over 2a. Quadratic equation. We have to solve using a quadratic. But all the same, we determine the moment of the day of the solstice using a mathematical technique and measurements that we take with a straw and a protractor. And we discover the moments of the equinoxes, the solstices, and the length of the year. And that brings us to the next talk, which is in 330 before the Common Era, Callippus noted that the length of seasons are not equal. Now, I previously went to pains to tell you that the seasons divide the year, the solstices and equinoxes divide the calendar of the year into equal 90-degree angle parts. But the sun seems to be moving faster in the winter, slower in the summer, and each season has a different number of days. Why? It should be exactly the same. So this poses a slight problem for the model as it stands right now. And the solution was proposed by a fellow by the name of Hipparchus. That's going to have to wait. That's going to have to wait. So because we've run out of time. It is a marvelous little trick that he uses, and it solves all the problems, which is why this system, the Earth-centered system, geocentrism, lasted 2,000 years without challenge. Because once we got these little problems that I'll show you next time hammered out, why there was no reason to assume that the sun was at the center. The system made astonishingly accurate predictions about solar eclipses, lunar eclipses, the positions of stars, hundreds of years in advance because it was so accurate. Any questions?
That really is very, very interesting. Yeah, it is amazing what they did that long ago, what they were able to, how insight, you know.
Mm-hmm. Anybody have any questions?
A lot to digest.
I know it was an awful lot, wasn't it?
Yeah, but it's great. I mean, you know, it takes me back to trigonometry and geometry.
I know it.
Which is
when are you going to give the next talk?
Whenever they'll let me back.
There you go.
Well,
We'll
they should
line it
let
up.
you back soon so we can digest all this, get up to date, and get the, you know, the get rid of the Earth-centered model.
Well, you know, the problem is because the length of seasons, this thing called the solar anomaly, because it is reality is not doing what we predict it should, we end up having to move the Earth in the geocentric model with the sun going around. We have to move the Earth off to the side a little bit, and it solves all our problems.
Yeah.
That's the mystery right there. An eccentric Earth solved all the problems. It allowed us to keep circular orbits. It allowed us to keep a sun that doesn't change its speed during a certain time of year. It solved all these problems. And of course, by preserving all these phenomenon, we were wrong because none of it's true. There are no circular orbits. Everything's elliptical. The Earth isn't at the center. The sun is. And the the Earth actually is changing speed at different points in its orbit. It speeds up as it gets closer in its orbit to its elliptical orbit to the sun, and it slows down further away. So all of it was wrong. And yet, because the model makes accurate predictions, it was really hard to find. It took Kepler and Tycho Brahe and Copernicus and those guys to finally figure out something's not right.
Amazing.
Well, thank you all for listening. I know it's an awful lot to throw at a person all at once.
George, we really thank you.
Yes, thank you very much.
You're very welcome. Thanks for having
Thank
me.
you.
Bye all.
Well, thanks all for joining us. Everyone have a very nice evening.
Thank you, Amy.
Thank you so much, Amy.
Thank you. Good job.
Bye now. Thank you. Bye, Sue.